So recording. Perfect. Okay. Well, here we go. Um, what's this? I do not have any Zoom poll questions today, so if you are here, you get credit for them. What we are going to talk about today is fundamentals or a fundamental of biochemistry, a fundamental building block of biochemistry, and those are our sugars. Now, these molecules are very important, and what we're going to focus on today is their structure. We're going to be looking at kind of what they can build up to, what the important terminology is related to them, and so we'll jump right into that. So, sugar, that term alone generally is in reference to, God, is generally references a small molecule, a simple molecule. Um, if you're using the term sugar at your dinner table or something like that, you're probably referencing glucose or fructose, which those are small molecules and they are simple molecules. Now, if you have ever heard the term saccharide, that's a little bit more broad of a term. And then if you've ever heard carbohydrates, that's an even more general and broad term because that includes your simple sugars. It also includes your saccharides. And beyond that, it also includes very large molecules. Now, when we talk about sugars, I want to tackle this term first. When we talk about a sugar, we're talking about the individual building blocks. So we've talked about polymers, and I want you to kind of frame our discussion of sugars in terms of polymers. Think about, and I'm going to say sugars, I'm going to put this as think about sugars or sugar saccharides and carbohydrates. Think about all of these as well, they can be a monomer or a part of a polymer. And I'm going to say a part of a polymer or a polymer. Now that's a little bit to me that last part, this right here, a part of a polymer or a polymer itself. That might sound a little bit confusing, but what I want to stress is that um, a if you've ever heard of a molecule like glycogen, well, I want you to know that glycogen is a polymer. It is made up of, well, it's lots of glucose molecules. It's also something that you can refer to glycogen as a sugar, or it is simply put as a sugar. Now, so that's where I'm getting at as a part of a polymer or a polymer itself. Could everyone give me a three in the chat if they follow that part of a polymer or a polymer themselves, and a seven in the chat if I'm a little bit confused by that. Okay. So when we talk about sugars and or a sugar and the individual building blocks, I want you to think about the monomers or a sugar being a monomer, which in this case we'd refer to that specific monomer as a monosaccharide, or we can take a couple of those building blocks and piece them together to make a small polymer like a dimer or a trimer, which terminology you'd associate with that would be a disaccharide or a trisaccharide. Okay. Now, this might be a little bit confusing because I started out with sugar, and then I brought in the second term of saccharide. Well, saccharide is a little bit of a more broad term, and it includes the monomers, but also large polymers of sugars, more than three of those building blocks put together. Now, the last term that you're maybe most familiar with is carbohydrates. And this is a term that has scientific relevance. It also has a relevance and significance. Um, it also has like day-to-day significance and relevance. If you go to anyone on the street and you say, "Hey, do you know about carbohydrates?" They're going to have a thought, or they're going to know something about carbohydrates. Um, and so I want you to keep that term in mind and not lose sight of it and think like, "Oh, well, that's just a, that doesn't matter to science." It absolutely does. Okay. Now, the first thing that I wanted, and so all of these terms, I will try to use them individually and say, okay, this is an example of a sugar. This is an example of a saccharide. This is an example of a carbohydrate. This you would not refer to as a saccharide, or how to fine tune those terms depending on the molecules. Okay, so the first name that we're going to tackle is monosaccharides. Monosaccharides are sugars. They are also carbohydrates. Now, thinking more generally, though, monosaccharides are simple molecules. In addition to being simple molecules, or as simple molecules, these are the building blocks for larger molecules, for polymers of sugars. These molecules have a basic formula of CX. What do we use X for in like any class ever? It's a variable. So, if you think about algebra, solve for X, it's going to be a number. So C and then a number. And then in parentheses, we got H2O and then another X. Okay. So if I said, so that's our basic formula. It's one carbon with one H2O. That's kind of a ratio. Now, does that mean that it's carbon bound to water? It does not. This is just showing the different atoms that are present and the ratio of them. So these get more complicated. These monosaccharides get a little bit more complicated when that X value is replaced with a number. Now, when it comes to monosaccharides, the smallest monosaccharides are going to be 3 carbons. So if I said, hey, I found this cool monosaccharide, CH2O, that's the formula, you'd be like, that's actually not going to be a formula. And I'll show you why or that's not going to be a sugar. And I'm going to show you why in just a moment. Now, when we substitute X for a value, that value is typically going to range, and whenever I say typically, I'm referencing the biologically relevant ones. They're going to range from 3 to 8. In addition to that, when we use this number 3 to 8, or this range of 3 to 8, let's go ahead and look at that applied. So I'm going to erase this right here, and I'm going to take my basic formula of CX, put in parentheses H2O, and then X. Whenever I substitute 3 for X, I'm looking at C3H6O3. This would be an example of it would be a sugar, it'd be a monosaccharide, it'd be a carbohydrate. All these terms are appropriate. Now, this specific sugar, you're going to use a prefix to describe it. And that prefix is going to be typically it's going to be just based on the number of carbons. This has 3 carbons, so we're going to use the tri prefix. Okay, so when we are identifying the number of carbons, we're going to use prefix like tri, C4H8O4 is going to be tet, Tetr, tet. It's really kind of difficult to pronounce an R, which doesn't have a vowel following it there with a consonant before it. Um, we're going to use that prefix, but you're not just going to call this tri-sugar or tet sugar. Instead, we're going to use a suffix. Use the suffix OSE. So, could you give me a one in the chat if you've ever heard the term glucose before? Now, glucose has that suffix, that OSE. But if you're looking at that and you're thinking GLU, that doesn't identify a number, you're not wrong. Glucose or gluc, that name is a unique name. That's a common name for a sugar. And I'll show you kind of how there are common names, but they can be classified in just a little bit. So where we go from here is we would say this sugar right here is triose. This one is tetrose. Now, glucose has 6 carbons. So that would be, well, hexose. Now, if you're thinking, do I have to know these prefixes? Yes, you do. I'm going to go with 3 to 8. So I'm going to label all these 3, 4, 5, 6, 7, 8. 3 is tri. I'm just going to label the prefixes. 4 is tet, Tetr. 5 is pent. 6 is hex. 7 is hept, Hept. And 8 is oct. So these would be triose, tetros, pentos. I think you guys get the point from there. All right. So when we talk about a sugar molecule, well, we're going to classify it based on the number of carbons, and we're going to use this term. Now, glucose, I'm going to write glucose down here. That is a common name for a specific sugar. And we're going to focus on glucose as our model. Glucose is an example of, since it has 6 carbons, it is a hexose. This is kind of like saying, I'm going to go ahead and erase that and say, glucose is an example of a hexose. So Y or N? Do you think that means there are other hexoses out there? Absolutely. There are other hexoses. So let me take that idea that you guys are all on and say, well, glucose is a hexose, but not all hexoses are glucose. This is kind of a classification and organization. Now, you might be looking at that and thinking, okay, so there's multiple hexoses. Are there multiple pentoses? Yep. Are there multiple tetroses? Yep. There are multiple variations of all of these different ones. Do I want you to know the names of all of those? Nope. Am I going to introduce you to those structures briefly? I didn't even add it to this slide deck because I didn't want it to be like, oh my gosh, I have to memorize those. That's not the point. I will want you to and expect you to know the structure of glucose, but that's pretty much the one. Now, for the next slide, when it comes to monosaccharides, We have one classification. I gotta erase that. I'm gonna say monosaccharide classification. And classification naming, I guess you could say, how you ask the question, how many carbons does the molecule have? That's kind of your first question. And if we look down at these two molecules, could anyone tell me in the chat how many carbons do they see? And this is going back to organic chemistry and skeletal structures. Remember the points or the intersections of lines indicate carbons. Tell me how many carbons there are. And I'm going to go ahead and start on the left-hand side. Get your wheels turning. There's one, two, three, four, five, six. Perfect. Now, this sugar on the left-hand side is a hexose. Now, the next thing that I want, there's a little bit of recall on this one. And if you don't remember that, or don't remember this, don't worry about it. But the next level of classification, after asking or answering the question, how many carbons does this sugar have? I think that all of y'all will look at these two sugars and say, they're different. And you're right. They're different from how they're identified, the names that are used for them, and they're different as an organic chemist would see them. This carbon, we would label this as carbon number one. That's carbon number one. And if you look at carbon number one of the things that I want you to notice is I'm going to draw these lines in red. Carbon number one has a carbon to carbon bond. Carbon number one also has a carbon to hydrogen bond. So it's sharing electrons with a carbon and with a hydrogen. Could everyone give me a 9 in the chat if they see that? If they follow those two bonds? Great. Now, we know that carbon likes to have 4 bonds. So two of them, one of them is to a carbon, one of them is to a hydrogen. And then we've got a first and second bond, a third and fourth bond going to an oxygen. So now this carbon, carbon number one, has a grand total of 4 bonds. It's sharing electrons with hydrogen, carbon, and oxygen. So it has 4 bonds, 2 single bonds, and 1 double bond. Now, this is a functional group, and this is known as an aldehyde. This is an aldehyde functional group. Okay. Now, I always like to just kind of, I think that it's helpful to say, what are our bonds? Our bonds are I'm going to say a C to C, then a C to H, then a C O. Now, let's move over to our next molecule. And if we look at carbon number one up at the top, well, not to discount it or be disrespectful, but it's kind of uninteresting. The interesting one is arguably this one, the second carbon. And in the event that you're looking at it, you're thinking, well, I think they're both interesting. Or you might be looking at it and saying, both of them are equally uninteresting to me. For this class, this one's interesting. This carbon is interesting. Okay. What I want you to notice is that this is I'm going to label it. I'm going to label bonds here. We have a C double bond O. So this carbon has a bond similar to carbon number one on the structure on the left-hand side, the aldehyde. Now, this carbon that has that double bond, I'm going to go ahead and draw my bonds again. I'm going to start with the double bond to the oxygen. That's 2 bonds. The third bond is a C to C. And then the fourth one is another C to C. Okay, could everyone give me a H in the chat if they see that? If they can kind of account for all of those bonds as well. Okay. This is an example of a ketone functional group. So we classify sugars based on, well, what functional group? Do they, I'm going to say have. I said display, but that's what do they have? What do they display? Both acceptable. Okay. Now, we use these two terms, aldehyde and functional group, representing the two different, um, these two terms representing the different functional groups to classify sugars. And when we do that, we come up with two terms. We classify sugars as an aldose or a ketose. Now, those are the two terms that we use to classify sugars. So this molecule, I think that, okay, let me take a pause. I think that it can be very helpful to look at these three, bonds that exist between that carbon, and same thing to identify our ketones. So you can look at it and say, oh, well, I'm not going to get tripped up. They both have a carbonyl oxygen. They both have a carbon double bonded to an oxygen. They both have at least one carbon-carbon bond. But what makes an aldehyde different from a ketone is that carbon-hydrogen bond instead of another carbon-carbon bond. Now, with that said, this sugar right here on the left-hand side is glucose. The sugar on the right-hand side is not glucose. Now, the sugar on the left-hand side that I've identified as glucose, which I will stand by, is indeed glucose. I'm going to try to move these. Is that how it works? Yeah. Oh, no. Um, there we go. This is indeed glucose on the left-hand side. Let's think about the names. Glucose is a hexose. Both of these are hexoses. Glucose is also an aldose. Okay, that is also true. And to consolidate those terms, we use something, or we kind of just throw both words in a blender. And glucose is an example of an aldo hexose. Glucose being the common name for this sugar, but glucose is an example of an aldohexose. So if you see an aldehyde functional group and 6 carbons, you're talking about an aldohexose. So between these two sugars, well, this one on the left is an aldohexose. The one on the right is not an aldohexose. It is a ketohexose. All right. Now, when we look at sugars, what kind of distinguishes them from one another, and I'm gonna duplicate this slide with all the markup and everything like that. I'm gonna focus in on my aldohexose. Delete all that. Now, format picture, crop, sign. Where is it? Well, doesn't really matter that much. Um, if I were to take this aldohexose on the left-hand side, our glucose molecule, and I were to take this hydroxide group right here, this alcohol, and put it on the right-hand side, I would have a molecule that looks like this. And I like to draw my carbons, so I'm going to draw my carbons. 2, 3, 4, 5, 6. So 6 carbons. I always like to draw my two, I like to fill in my first and sixth carbons with all of the shared electron pairs that make them kind of have complete octets. And now what I'm going to do is reposition the hydroxide groups. I'm going to keep on carbon number 2 the hydroxide group on the right-hand side. Carbon number 3, I need to move that hydroxide group from the left to the right. Carbon number 4, I'm going to keep OH on the right-hand side of my molecule. Same thing with carbon number 5. Okay, so, ah, well, let's count this up. I got a private message of galactose, and I like what you're thinking. Okay, so galactose is an example of an aldohexose, and I'm going to get into galactose in just a moment. Sounds like I'm going to start selling it. I'm really getting into galactose, or I'm going to, I don't know, like I'm getting into Dungeons and Dragons and galactose. Um, this is not galactose. Could you tell me, anyone in the chat, which carbon number did I move the OH group on? And identify it like C1, C2, C3, C4, C5 between these two figures on the right hand side. Yeah, C3. Okay. Now, this is where we're going to bring in a pretty important term that I want you guys to really be comfortable with. And before I do that, though, I got to draw a shape because I want to block this out so it's not a distraction. Shape fill, white. Shape outline, white. It's like it's not even there. Amazing. Okay. So what I did was I made one variation. This is a C3, and I use this term, epimerization. The relationship between these two sugars is that they are C3 epimers. Now, of all of these sugars that I want you to know, I only want you to know the one on the left-hand side. I want you to know that structure. That is glucose. On the right-hand side, this happens to be a sugar with the common name of allose. So it would be a fair statement to say that glucose is the C3 epimer of allose. Okay, that statement is true. Now, notice how there's arrows going forward and backward. It is equally true to say allose is the C3 epimer of glucose. So we're comparing allose and glucose to one another. What makes them different? Well, where is that hydroxide group on carbon number 3? This one right here. Well, in glucose, it's on the left-hand side. In allose, it's on the right-hand side. Now, I want you to know this term, epimer. I want you to be comfortable with that term. I don't need you to know how is allose related to glucose, But I do want you to know if you move one of those hydroxide groups on glucose, it's no longer glucose. What is it though? Now, I bring that up because if we were to take, and I'm going to duplicate this slide again, and I'm going to get rid of my structure of allose and some other things. No, I don't want to get rid of all of that. I do want to get rid of that. Yeah, it's there. Get rid of this. Because what I'm going to do now is I'm going to go in and put together the same sort of information relating glucose to something else. And that something else is galactose. Now, galactose is still an aldohexose. Allose is an aldohexose. I've got my chain of 2, 3, 4, 5, 6 carbons. Galactose and glucose are C4 epimers of one another. So I'm going to erase that, and I'm going to say, well, this is a C4 epimer. So again, I'm comparing glucose to this other sugar. So if I go carbon by carbon, looking at number 2, we've got OH, H. Left-hand side, OH, because I am not changing that. I'm relating glucose, my initial structure, to this new one, and H. The only difference that I should see between these two sugars is what is surrounding carbon number 4. So this is galactose. Now, when you look at sugars and you're trying to kind of piece something together with respect to them, I think that it's really good to look at it and say, okay, well, what am I changing? Epimers are unique in that they differ from one another because of one carbon. The only difference between them is what surrounds one carbon. So if you move hydroxide groups on 2 different carbons, you're no longer talking about an epimer. Now, so the takeaway from this is I want you to, these last 2 slides, is I want you to know the relationships as they pertain to epimers. I want you to be comfortable with that term of epimer. Now, the last carbon that I want to reference here, and this is an important one, is I'm erasing my epimer. Whenever you look at a sugar, a linear sugar like this, there is one carbon that you always have to look at. Okay. Now, if we are drawing glucose, we've got a total of 6 carbons. Carbon 1, 2, 3, 4, and 5. Okay. So could you tell me what is the second highest, or no, let me rephrase that. Second to last carbon number in glucose. You're counting from the top down. What's the second to last carbon number in a 6 carbon sugar, in a 6 carbon molecule like this? It's a clunky question, but Victor, you're absolutely right. Carbon number 5. Okay, so I'm going to say that this is C5. Okay, now if I were to show you this structure right here, I'll go here, H2OH, OH. Okay. Dang it, Joel. Okay, look at this sugar right here. What is the second to last carbon number in the sugar on the right? Give me that same response as C something. or the second highest numbered carbon, C3. Perfect. Okay. So this would be C3. When you look at a sugar, when you look at a linear sugar, you always want to look at what is the second, I'm going to say, second highest numbered carbon. That's a question you always want to ask yourself. So let's take you guys have done C5 and C3. If you're looking at an octose is 8 carbons. So the second highest numbered carbon would be carbon number 7. Okay. What about a heptose? Well, the second highest numbered carbon would be carbon number 6. Could you give me a Y in the chat if, okay, I follow that. I could do that. A Y or N. Y being yes, I could. And I can. I know how to do that. Great. Now, this is a very significant number because that second highest numbered carbon, whenever we look at a sugar, we always want to look to that one when it's in its linear form, because then we're going to look at the OH group. Is it on the right-hand side or is it on the left-hand side? And the reason that we do that is because if the hydroxide group on the second highest numbered carbon, so we're going to look to the second highest numbered carbon and say, where is the OH? Question mark. If it's on the right, that sugar is considered a D sugar. If it's on the left, that sugar is considered an L sugar. And that is very significant because D sugars get metabolized. Your body and all the enzymes that are in your body that break up sugars, that consume sugars, they can distinguish the difference between a D sugar and an L sugar. And when they see a D sugar, they say, oh, fantastic, I can get energy from that. When they see an L sugar, they say, well, I can't do anything with that. So it goes on. Now, I want to show you an example of an L sugar, and I'll do it right up here. And we're going to talk about this one and come up with some classifications. Every time you draw the display, we'll see one be the CCCO and CH. I got a private message that I think is asking about carbon number 1 and the bonds that it has. Whenever I'm drawing carbon number 1 with a carbon-carbon bond, a double or a carbon oxygen double bond, and a carbon hydrogen bond, when carbon 1 has those, that would be an aldehyde. So that would be an aldose. If I draw it differently, then it's not going to be an aldose. I focused on aldoses because glucose is an aldose, and that's kind of the sugar I want you guys to focus in on. I hope that answered your question. Okay, so I'm going to show you this right here. And let's talk about this sugar right here. And we can classify it. First classification. How many carbons does it have? Well, it's got 1, 2, 3, 4. That is a tetrose. Okay. Next question. What functional group do we see? Well, this question that I got as a private message was asking about carbon number 1 with different bonds. There's a carbon-carbon bond, a carbon-oxygen double bond, a carbon-hydrogen single bond. So that would be an example of an aldehyde. So this is an aldo tetrose. Could you give me a 9 in the chat if you're good with, oh, I followed that it's a tetrose. I followed more specifically that it's an aldotetrose. Great. Now we can take this one more step for classification. And we can look at the second highest numbered carbon. This has 4 carbons total. Carbon 4 would be the highest numbered carbon. Therefore, carbon 3 would be the second highest numbered carbon. So we are looking at an aldo tetrose, but more specifically, an L aldotetrose. Okay. Now, I want to go ahead and draw another molecule, and I'm not going to draw it where it's running over everything, but I'm going to erase this, give myself a little bit more space. So we've got another sugar right here. I'm switching it up a little bit. And let's go question by question. First, how many carbons does it have? 5. So this is a pentose. Okay. Next question. What functional group do we see? Well, we can answer this question by, yeah, Elena, you're absolutely right. This is a ketone. And if you're like, well, I got comfortable with the other one. I mean, you could treat that as, well, it's not an aldehyde, or it's so it has to be a ketone, and you'd be absolutely right. If you want more comfort with the bonds that you see in a ketone, carbon carbon, carbon oxygen, carbon carbon. That. So that's a ketone. So this is a keto pentose. Now the last question is this an L or a D ketopentose? And do we care about this hydroxide group? Nope. We only care about this one right here. This one that I put a box around is going to tell us that it is a L ketopentose. Now, if you saw this molecule, and then I'm going to switch it up, and instead you saw this molecule right here, and you were asked about that. Well, what makes this different? Does this term completely apply to this molecule? It does. Are those two sugars the exact same? No, they're not. But in terms of, are they both pentoses? Yes. Do they both have a ketone? Yes. Are they both L sugars? Yes. So these are both L ketopentoses. Could everyone give me a 6 plus in the chat if, yes, I understand that? Right. Wonderful. Okay, so the next place that we're going to go is we're going to look at sugars and how they're kind of more realistic and more relevant to a cell. We're not going to see them as straight chains. They're instead going to form rings. Now, these rings, like this right here, are an example of what's known as a Haworth projection. Now, I'm going to draw the bonds that make up the ring itself. And I want you to kind of look at that as this is a flat surface. And what I mean by that is rather than looking at the, you know, I always kind of think about it like a table. And this, what I've just shaded, is the top of the table. Now, I'm going to give you another rendering of this. I like using the word rendering. Rather than you seeing everything, imagine that you're looking at it. That's poorly drawn. Imagine that you see kind of this view right here. You're looking at the side of a table. When you look at that side of the table, you're going to see CH2OH coming up and then OH going down. So I just drew this here, and then I'm going to put a box around this OH. That is this OH. Then this one, I'm going to put a circle around this OH. that is going up, then the boxed OHs are pointed down. So whenever you see this structure right here, try to translate it into something that looks like this. Can you give me a 8 plus? If yeah, that makes sense. I can visualize that. I can make that jump. Or I can take that step. Okay. And if you can't, that's fine. Now, what I want to do with you is I want you to kind of follow how a linear sugar translates to a ring. It's not trivial. Now, I need to show you guys something, and that's something that I need to show you. I'm going to show you on the next slide here. Okay. Um, okay, so there's one sugar that I want you to know really well, glucose. Whenever I'm drawing glucose, the way that I think about glucose is I start at the top and I draw my aldehyde functional group. And then I start basically speaking to myself and saying where my hydroxide groups are. And whenever I describe and I'm giving myself the instructions for drawing glucose, I say right, left, right, right, left, right. Now you might be thinking, oh, but wait a minute. I'm not done. And I'm not. And then you might pause and say, oh, but what about carbon number 5? Well, I don't count carbon number 5 because carbon number 5 is kind of, it's almost like you keep it out of the equation. You keep it out of the consideration because carbon number 5 is going to tell me, am I working with a D or L sugar? So my default is to the ones that are biologically important. Could anyone tell me the single letter for which sugars are more important biologically, D or L sugars? Which ones get metabolized? London, you're absolutely right. D sugars get metabolized. So those are the ones that matter. So whenever I'm drawing glucose, I'm drawing D glucose. So I'm going to put my hydroxide group on the right-hand side, hydrogen on the left, and then carbon number 6 is going to be CH2OH. And I'm done. Now, when you look at this structure on the left-hand side, and you look at this structure on the right-hand side, I'm going to highlight a carbon and show you where that is in the ringed version. CH2OH, it's right here. So that's carbon number 6. Now I'm going to circle a carbon, and you tell me what carbon number do you think that it is? What number? It's not 6, so it's got to be 1 through 5. And take a pause and say, well, I know that carbon number 6 is bound directly to which carbon number? 5. You're absolutely right. So this carbon is 5. Now the next one that I'm going to circle is this one right here. Tell me which carbon do you think that is? 4, 3, 2, and last but not least is 1. Okay. Could you give me a emoji in the chat if, okay, I follow that, or I'll accept those numbers. I can wrap my mind around that. I like the handshake. Okay. So we've got these different carbons. And I'm going to go ahead just to keep track of everything. I'm going to label them on the linear form too. 4, 3, 2, and 1. Now, looking at those carbon numbers, nothing has changed. It's not like when you go from the linear form to the cyclic form, carbon number 4 becomes number 2 and 1 becomes 6. Nothing like that changes. Okay. When it comes to looking at glucose, we've got these relative positionings of our OH groups. Right, left, right. Okay. How would you translate or transcribe the positions of the OH groups on the linear form to the cyclic form? And what I mean by that is right up or down? Is left up or down? And what I want you to do is narrow your focus to these 3. And in order to do that, well, let's see. We know that carbon number 2 and number 4 will have hydroxide groups on the same side. In this case, when it's linear, they're on the right side. Okay. When it's the ring, carbon number 2 and carbon number 4. So here's 2 and 4. They both have OH pointing down. So then carbon number 4 has an OH pointing down. So another way to translate that is to say right, and I'll give a little bit more of a statement. In linear structure, right translates to down in the ringed structure. Okay. Can everyone give me or just say N if that doesn't make any sense, so they can't wrap their mind around this. And it's not a really well-written statement or sentence, so I apologize for that. But if right means down, then left means up. Question, why are the OHs on 4 and 5 in different positions on cyclic structure and not the linear? Questions of OH. In different positions in cyclic structure. Okay, I got a fantastic question. Why are the question is about the hydroxide groups on carbons number 4 and 5. Now, before I get into that, I want to tell you that these things are important for carbons or OHs on carbons 2, 3, and 4. Now, the question that I got, why are the OHs on 4 and 5 in different positions on the cyclic structure and not in the linear? I interpret that to mean, well, in the linear form, the OHs are both on the right-hand side for carbons 4 and 5. In the cyclic version, we've got, well, heck, This oxygen right here, that's that's a part of the ring. And that's a very important thing to recognize. I'm happy that you did. So what happens whenever we cyclize a sugar? And please don't hesitate to tell me if like, no, you're not getting my question. Um, when we cyclize a sugar, we have to have an OH group become a part of the ring. So the OH group that becomes a part of the ring, this oxygen right here is this OH group. Now you might be looking at that and saying, well, this is an OH group. This is an O. What happens? Could everyone give me a 7 in the chat if they're following all of this and looking at this and they're saying, yeah, what gives? How's that happening? And then a 1 in the chat if I'm flustered. Okay. Now, whenever that happens, I want to draw your attention to, I'm going to go with a highlighter. Let's look at what is bound to carbon number 1 in the linear form. We've got a double bond going to an oxygen, and we got a single bond going to a carbon, and then we got a single bond going to a carbon. Okay, I'm going to clean this up a little bit. I'm going to do some erasing. Go, there we go. Yeah, there we go. Okay, and now what I'm going to do is I'm going to draw, I'm going to highlight, pick an obvious color, highlight, there's carbon number 1. And I'm gonna be asking for lots of responses here. Give me a 1 in the chat if you're good with that being carbon number 1, and you see that. There's carbon number 1 in linear form. I want to focus in on carbon number 1 in the cyclic form. Okay. Now, here is my carbon-carbon bond in the linear form, and here is my carbon-carbon bond in the cyclic form. Give me a 3 in the chat if you're good with that. Okay. Now, the hydrogen, this is something organic chemists do, is whenever they have a hydrogen, they don't really draw it, but for the sake of this, there's your hydrogen. So we've accounted for a couple of things. We've accounted for the carbon-carbon bond right here. We can match that. I see it now. C1 has 2 oxygens bonded, not just the same one. Spot on, 100%. Carbon, we can account for the carbon-hydrogen. Done. Now, whenever we look back at the linear form, we've got carbon double bonded to 1 oxygen. So that's 2 bonds to 1 oxygen. Now, if you're looking at that, and then you're looking at the ring structure, you're probably saying, well, here is a single carbon oxygen bond. Here is another single carbon oxygen bond. How's that happen? Well, what this carbon does, and I'm going to switch colors to, let's go with black. This carbon comes down here and makes a bond with that oxygen. And that oxygen over that OH group. That OH group loses the hydrogen, which then this oxygen picks it up. So this oxygen right here becomes this OH group. This oxygen right here is this oxygen. So it's almost like these 2 oxygens, the double bonded oxygen and the OH, they just, one of them gives up a hydrogen, the other one accepts it in order to make that ring structure. That's what happens in order for this structure to become a ring. Okay, so moving on from there, I want to now talk fairly briefly about the polymerization of sugar. Sugar polymers form through bonds known as glycosidic linkages. Through a reducing end and a non-reducing end. Now, what I'm going to show you guys is actually, I think that I have a, yeah, so perfect. Uh, the only problem with using a white pen is it's with a white background is it's very easily lost. Okay, so I've erased that hydrogen. I've erased that hydrogen so that what I can do is draw in a glycosidic linkage. Actually, you know what? I'm going to take it a little further. So I've erased that OH group. I'm going to circle this end right here is considered to be, or is known as a reducing end. So as kind of a primer, when you're thinking, oh, I want to find the reducing end of a sugar, what I want you to look for is this right here. So this would be carbon number 1 right here. That carbon number 1 has a single bond to an oxygen. That's a part of my ring and an OH group. So when you're like, oh, what's a reducing end? Look for this right here. Can everyone give me a 5 in the chat if, okay, I know what to look for. Now I'm going to highlight in a different color what is typically known as the non-reducing end. This right here is typically known as the non-reducing end. So I always think about a reducing end as being the right side and the non-reducing end being the left side. All right, now I've replaced that OH group. And what I'm going to do is I'm going to draw another glucose molecule, or basically the buildup of another glucose molecule. So at this point in time, I've got the same ring structure, same 6-membered ring. Carbon number 1, I'm going to put this OH group here. Now for carbons 2, I'm going to put the OH group down because in order for this to be glucose, that OH group has to be pointing down. Carbon number 3, my OH group has to be pointing up. Okay, so with these two structures, or the one that I just drew, I have accounted for all of the atoms in glucose except for the OH group on carbon number 4. Can everyone give me a 3 in the chat if, yeah, I see that. I've got it. Okay. Now what I'm going to do is show you guys the what's known as a glycosidic linkage. I'm going to switch colors to, I'll go with this blue pen. I'm going to draw an oxygen. That oxygen is going to connect carbons number 1 of the glucose on the left-hand side and carbon number 4 of the glucose on the right-hand side. So this is known as a glycosidic linkage. Now, when you look at this, this is known as a disaccharide. Can you answer me? Okay. And now what I want to emphasize is let's go back and look at this molecule and look for the reducing end. Now, when we look for a reducing end, we're looking for this oxygen, a carbon, and an OH. And I'm stressing those 3 things constitute a reducing end. So let's start with the sugar that we've drawn in black. And I'm going to highlight these with a nice, let's see, pale blue. Here's oxygen. Great. Here's my carbon. Great. Do I have an OH group there? Y or N to the chat. Nope. I have an oxygen, but is an oxygen the same as an OH? It is not. So give me Y or N in the chat. Is what I just circled in pale blue, is that a reducing end? No, it's not. Okay. So thus far, when we've looked at this molecule, we see zero reducing ends. Now let's go on to the remainder of this molecule. There's an oxygen. Great. Here's a carbon. Great. Here's an OH group. Aha! That is a reducing end. So how many reducing ends do we have of this sugar? One. Great. Now, for a non-reducing end, we're looking for something like this. And we're going to go with organic chemists and say, we don't need to draw that hydrogen. We're just looking for an OH group. Here's an OH group. There's a non-reducing end. Okay. Those are the things that you want to look for. The last thing that I want to do is I'm going to draw another glucose molecule. And actually, I'm going to draw a branched sugar molecule. Okay, so here is my basis. It's my glycosidic linkage that I just drew in. I've drawn one reducing end. Great. CH2 OH. Okay. Here's my CH2. I'm going to go ahead and fill in the rest of this OH. So I'm still OH, OH. This sugar on the right, I'm going to draw a little different. Okay. Now, this disaccharide that I've drawn so far, I want you to be thinking about, well, what are potential questions that he could ask? One, does this show two sugars within a disaccharide that are epimers of one another? Yes, it does. These two sugars are C3 epimers of one another. Next up, does this sugar on the right-hand side, this whole thing, does it have a reducing end? It does, because I see that OCOH. Now, the next thing that I want to do is this right here. Okay. So what do we have in terms of good descriptors for this molecule? Is this a reducing, or does it have a reducing end? And I'm gonna make this like a running tally. Um, and I know what to look for my base of my reducing end. I'm looking for an oxygen, carbon, and an oxygen. That's not a reducing end. Oxygen, carbon, oxygen, we know that's not a reducing end. Oxygen, carbon, hydroxide, that's a reducing end. So we have one reducing end. Now, this right here, that end of a sugar is typically going to be your non-reducing end. And we've got two ends that look like that. I'm going to label this as NR, or non-reducing ends. How many non-reducing ends are there? Well, there are two. There's one reducing end and two non-reducing ends in this sugar. Okay. Does that make sense for anyone? Or actually, if that makes sense, could you add a 5 to the chat? If you have some confusion about reducing and non-reducing ends, add a 9 in the chat. Or send me a private message. That's where I'm going to stop for today. I'm going to save all my markups on this, and I'm going to upload this marked up slide deck to our Canvas page. I'm going to upload it as a PPTX file. And the only reason for that is the PDFs. All right, I've had issues whenever I save all the markups and then make the PDF. The markups don't seem to go with it. But with that said, thank you guys very much for coming. Thank you for your participation. If you've got any questions, please don't hesitate to ask. Other than that, I will see you all on Monday. So enjoy your weekend.